So validation and cross-validation we actually talked about in quite a bit of detail in the section along with the bootstrap. So I won't cover it in much detail now, just to remind you. So the basic idea is now, well, the basic problem, right? We have a sequence of models, like, for example, from subset regression, forward stepwise or backward stepwise, each one with a model size k, and we want to choose the best model size. We just talked about some methods based on adjusting the RSS, CP, AIC, and BIC. Validation and cross-validation, rather than making an adjustment, they're more direct. So just to remind you what the idea of validation is, we divide the data up into two parts, a training set and a validation part. So let's just draw that. So here's my training part at random. Maybe I'm going to choose, say, a half or 3/4 to be my training set and the balance to be the validation set. And then the basic idea is we're going to fit the models of various sizes, of various k. For example, if it's forward stepwise, I'm going to choose I'm going to find that the best model of each size, the forward stepwise model of each size k on my training set, and then evaluate its error on the validation part. And the validation error as a function of k will be what I use to estimate prediction error and to choose the model size. So this is validation, and the cross-validation is much like that, except it's sort of a k-act play, right? So if it's five-fold cross-validation, I'll divide the data up into 5 parts, 2, 3, 4, 5, and then at each stage of the play, 4 of the parts are training sets, are the training set. So let's say these first 4 parts are the training set. And this last guy is the validation in this phase. So I will fit the models of all size k to these 4 parts of the data, the training set, and evaluate the error on the validation part. And I'll do that in turn for the 5 different possibilities, where at each stage, one of the pieces is the validation and the other 4 pieces are the training. And then we'll summarize the results together to get an idea of the error as a function of k. That's called the cross-validation error estimate, and then we'll find the minimum of that curve. So again, I said that quickly because we've gone over that in detail in the previous section of the course. So here I've said this again in words on the second bullet item. So either using validation or cross-validation, we'll get an idea of the error for each model size k, and then select the k that gives us the lowest test error over the validation part of the process. And this is actually a very attractive approach. And we've said this already, but it's good to say it again. Compared to the other methods we talked about, the advantage, there's a number of advantages. The one big advantage, it doesn't require an estimate of sigma squared. You might think that's a small advantage, but it's actually quite important, because if p is bigger than n, as it is quite often in data that we see these days, to get an idea of an estimate of sigma squared is very difficult. We can't fit a full model, because the full model will totally saturate and give an error of 0. So we have to pick some kind of a smaller model, but it's quite arbitrary, the model we pick, and it's hard to know. We'd like to fit a model that has all the good variables and leaves out the noise variables, but we don't know, of course, what's the signal and what's the noise. If we did know that, we wouldn't even have to fit any of these models. So it's getting an idea of sigma squared. It seems like it may be a trivial matter, but it's actually very challenging for models for situations with large numbers of features. So,
and that's actually challenging to the point where it's an open area in statistical research. So I'm an associate editor for a journal, and we get submissions from statisticians at top tier universities who are coming up with ways to estimate sigma squared. So maybe in 10 years this will no longer be a challenge, but right now it's really hard to do.
Right, and that's actually one of the reasons it's so much fun to be a statistician, because we get new kinds of data, for example, high dimensional data with large numbers of variables, and it presents challenges to things which were simple with small numbers of variables now become very challenging, but very important. So the technology and the kinds of data that we see bring new challenges to our field every day. So cross-validation helps us solve that problem by avoiding an estimate of sigma squared. We don't need to plug in sigma squared anywhere. The other point is you don't need to know d. Remember these previous formulas, for example, the adjusted R squared had a d in it, and CP and AIC and BIC all had the number of parameters. Well, again, that might seem sort of a silly thing. Well, of course you know the number of parameters in your model. Well, that's true when your model is a linear model and you're choosing predictors as coefficients. But for methods like ridge regression and lasso, which are shrinkage methods we'll talk about next, it's not at all clear what D is. And it's another whole area of research, figuring out what is meant by D, the number of parameters, in a model which is not fit by least squares. So again, cross-validation finesses that problem by not requiring you to plug in a value for D. So D and sigma squared are both challenges, and cross-validation relieves the worry of having to come up with good estimates of those. So I've said all these things. So let's see what it looks like in the credit data example. So again, the number of predictors. Here we plotted the square root of BIC just to make it comparable to the other two estimates, the validation set error and the cross-validation error. So here we did, actually, validation set was 3/4, 1/4. So 3/4 of the data was randomly chosen to be the training set, 1/4 is the validation set, and we see the error tracked as a function of the number of predictors. We've marked the minimum, and here it's about 6 predictors. Cross-validation, I think this was, do I say here, 5? A 10-fold cross-validation. We like 5 or 10-fold cross-validation in general. They're good values. It's producing about the same model size, 6 as the minimum. Again, the curve is very flat. It's hard to see here. It's rising very slightly to the right. But there's not much to choose between, say, 4 and 11 predictors, right? They give you basically the same error. BIC, as is often the case, remember we said compared to AIC, it imposes a stronger penalty on the model size. It tends to produce models which are a little bit smaller, and it did so here. Here it's about 4. But again, the curve is so flat, there's not much we can really say about these models between 3 and 11 predictors. And actually, I mentioned the bottom here, the one standard error rule. We talked about this a bit in the cross-validation section. Let me just remind you what that is. The one standard error rule says, well, we're not going to pick the actual minimum of the curve, but we'll acknowledge the fact that the curves have variation, because they're random variables, just like the data are. They're functions of the data. So the one standard error rule, let's draw it just in pictures here. So let's suppose we have one of these curves in the minimum. Here's the actual minimum. The standard error of the curve, which we didn't indicate in these examples, but we should have, we can get, well, the cross-validation just an average over the k folds. So the standard error of that mean of k, things like k is 10, the standard error of those 10 numbers, gives us the standard error of this curve. So we could draw the standard error, plus or minus 1 standard errors from the minimum. So the one standard error rule says, remember this is the number of predictors along the horizontal axis. It says don't choose the minimum, but take the simplest model that comes within 1 standard error of the minimum. So that would be, we'd come across to here, and we choose this model. Okay? So the idea being, well, if these models are within 1 standard error of each other, we really can't tell them apart on the basis of the data, because the error is almost the same. So all else equal, we'd rather have a simpler model. So that's why we've moved to a model to the left here, which has fewer predictors, and its error is no more than 1 standard error away from the error of the best model. So the one standard error rule, which is pretty popular now, is to not use the model with the absolute minimum, but use a simpler model that comes within 1 standard deviation of the minimum. Okay. So the rationale for this, again, I've said it, is that if the models are within 1 standard error of each other, let's choose the simplest one, because it's easier to interpret.